Hi everybody, I'm Professor Adam Teman of the EnICS Labs at Bar-Ilan University, and today we're going over the fifth part of my demo on RTL2GDS. This time we're going to take a simple SoC and run an example of a full RTL2GDS flow. It's going to be much more complex than the previous ones, but it's still a very simple SoC. So let's start with a short introduction. In the previous parts of the series, I covered RTL2GDS on a simple block. We did everything pretty much. We understood the RTL, we ran directed tests to verify functionality, we ran synthesis to get a gate-level netlist, we ran gate-level simulation with timing back annotation, we ran vector-based power estimation, and finally, we ran place and route. However, our place and route flow was a bit too easy. We didn't have any macros to deal with, we didn't have to create an I/O ring, everything was small and simple. So now we're going to go for a slightly more complex design. A real SoC, I would say. I just want to point out here that if you have not watched the previous parts of the series, I really recommend doing so. I'm not going to be going into the same depth or in the same introduction on each and every part, so this is kind of a more advanced one. I am going to reiterate on many of the things I already said, but now we're going to see it in a kind of more complex example. So I really say that you should go back and watch the previous parts before starting with this one. So let's have an overview of the simple SoC that we're going to be working with. A SoC is a system on a chip, which basically is a chip with various different components, including control and memory. In this case, we're implementing a tiny SoC. All it has on it is a CPU. In this case, it's a small RISC-V core. Some memories. In this case, we have instruction and data memories that are tightly coupled to the CPU. And we have inputs and outputs, IOs that let our chip communicate with the outside world. It's a very minimal and basic SoC, but it's really a wonderful example. It's a real working system that can run compiled C code, and I'm going to show you that. It has RTL files that make up many of the modules and pieces. It has SRAM blocks that need to be placed in the floor plan, so this time we have real hard macros that we need to deal with. And it has IOs that need to be constructed into a functional IO ring. Let's talk about our SoC. It's going to be based on a RISC-V core from the Pulp group, the RISC-E core, and you can see the website over here to look better at this RISC-E core. But in general, it's a very simple embedded embedded core. It has a 4-stage pipeline, so we have instruction fetch, instruction decode, execute, and write back. It's really pretty simple. But the interesting thing about it, it's a full working CPU that does a lot of stuff. And what we're going to do is we're going to connect to it an instruction memory and a data memory in a Harvard architecture, as you can see here. So this is going to be the core inside. We're going to have our memories, and we're going to surround that with IOs. So we're going to have IOs, a whole IO ring around here. So this is a complete chip. It's a complete system on a chip. A real simple one, albeit, but it still is a system on chip. So I'm now going to overview our design itself, show you kind of what it is, and then actually prove to you that it does something, that it really works. What we saw before is if I go into source code, I have my RTL and my TB. And in RTL, I have the SoC, which is basically the top wrapper that has inside it a RISC-V core that is connected to a couple of memories, an instruction and a data memory, and connected to pads that will bring it to the outside world. Inside RISC-V master, we have the actual RISC-V core. So just looking inside here, all these files are the files of the RISC-E, with RISC-V core being the top level of the core itself, which we'll look at in a moment. But starting from the top level of the whole design, we go into SoC and we have this LP RISC-V top file. And so let's look at the LP RISC-V top file. And so it's a module that all of the interface of the module starts with pad, and that is for the pad, that little piece of metal that is connected to the IOs. So these are the names of the IOs, and we put them just in uppercase to show that these are the outside world. Looking at what we actually have here, you see we have a list of inputs and a single output. The output is the done flag. The inputs are the clock enable, some performance counters, some other stuff that has to do with the memory, and a reset and a test enable pad. Okay, and the output is the done flag. All the top is actually going to do, it's going to instantiate the IOs themselves and connect from this pad input to an internal wire that's going to go into the other components of the core. So for that, we defined all these wires, such as clock to core, clock enable to core, done flag from core, etc., etc. So we have all of these that go from basically the IOs to the core, and they're called to core in that way. And then we have the instantiation of the IO ring. And all the IO ring is doing, it is connecting to ports that are called the same thing as the pads. It's connecting the ports, and then it's outputting wires from that. So from those IOs, basically, we would do something like a wire bond, taking the connection from the inside world of the VLSI to the outside world of a package, and the package would be connected to a board. So this is wire bonding, and this is our chip here will set this up. And that is enabled by what we call an IO ring. So the IO ring connects to the outside world, which is off-chip, to the SoC, which we call on-chip. And for this, we need pads. These are big pieces of metal that we can connect the wire bonds to. So remember, everything in VLSI is very small. It's much smaller than machinery can actually deal with. We do this with our, integrated circuit process. But we need to go over to the real outside physical world. And so we put these big pieces of metal that we can connect wires to. We have digital IOs, which are buffers that contain level shifters and ESD protection. We have analog IOs, which are just basically wires that have ESD protection and they connect to the outside world. And we have power supply cells, which are IOs for connecting the bias voltages to the chip. The digital IOs just propagate signals. They don't carry out logic. With these digital IOs, we have external signals, and they're connected to the pad. So the pad is this piece of metal, again, it's on the chip that enables us to connect a wire bond or a bump or something like that. But it's a bigger piece that can connect to real machinery. And therefore, we call the inputs and outputs, and this is methodology, we call it pad with a large PAD here, and the name of whatever our input is. We use capital letters for that to show that these are our primary inputs and outputs to our chip. The internal signals that go from the actual IO into the chip itself, it connects to the core. So we call them, whatever the name of the signal is, to core, and here we use lowercase letters. We have a file called ioring.v, and it instantiates IOs from the library. This is not synthesized, so it's basically a structural model. We put instantiations of the exact IOs that we want to use from the library. This is something that we select. So let's see what those types of IOs that we have. And this is generic, any IO library would have something like this, but let's look at the ones we're going to be using. So first of all, we mentioned that we have these digital IO cells. And a digital IO cell is going to enable us to do input and output of digital. So it can drive a 0 to the output of the chip, or drive a 1 to the output of the chip, and it can accept a 0 or 1 at the output of the chip, from the output of the chip to the input of the chip. Now remember that inside the chip we're going to be using low voltages, and this is what we call the core power domain. So everything on this side of this schematic is going to be on the core power domain. It can be 1 volt or 0.8 volts or 3.3 volts, depending on what our technology is, but it's usually going to be lower than the voltage that we have outside the chip, which is going to be the IO power domain. So everything that goes through between these two has to go through level shifters. And what else do we have here? Well, we have a whole bunch of signals. So we have this pad connection, and again, this is specific to the IO library that we're using, but in whatever IO library you're using could have different names, but this is just a general type of way to do it. So the pad is the connection in the IO cell that we have that connects to that pad, that piece of metal that is going to connect to the wire that goes to the outside world. And as I said before, this is going to be using capital letters, starting with pad and then whatever the name of the input or output is going to be. Okay, then we have a bunch of different things. So if it's an input over here, we're going to connect whatever signal it is. It's going to go into this buffer over here, this level shifter, and come into our chip. In this technology, in this library, we call the internal connection C. It could be called anything. And we're going to connect the wire that's going to be going to core. And again, it's going to have the same name, usually my input, and then to core, and that's going to be in lowercase letters. So these are the signals that we're just connecting this signal to here and going through a level shifter. Okay, if we're using this as an output, then we would connect some sort of signal to out or something like that over here, or we would call it to core anyway, but it's going to be an output that goes from our from our core domain to the outside world. It's going to connect to this I connection, it's going to go through a level shifter that's going to take it from our core voltage to the IO voltage and to the pad. Now the thing is that we cannot have some sort of a conflicting connection. So if we want to use this as an output, we put this output enable. It's a low active signal, so output enable 0 would enable this buffer over here, and then we would be driving to the output. Since it's an input, we're going to put a constant 1 here, and it's going to turn off this tri-state buffer. Okay, so there is no problem if we use this as an output to have the input and we can connect anything to here. That is not a problem. The problem is that if we were driving an input from the outside and driving an output from the inside, these would be conflicting and we can't have that. So these are basically the signals that we will have on a digital I/O cell, and we're going to select such a cell from the library and connect these types of things. And this is again going to be done structurally. We have our ioring.v file. It's going to have all these signals are going to be written by hand. This is there aren't many of them, but we do this really manually. So when we look at one of these IO cells, they actually have a specific structure, and this is going to be true for, I guess, all of the IO cells, not just the digital IOs, but so let's see this. What we have here is we have the pad that connects to the outside world. So this is going to be a different actual like LEF or a different GDS. It's just basically a piece of wire that's rather big, and it has vias underneath it and more metal layers and so forth. So when we do a wire bond, we're not going to mechanically break this and cause an open or something like that. And so this is a pad. It's going to be different with the flip chip design. This is on a wire bond design, which we are playing with, but it's just, again, it does nothing. It's just a wire, and that's the pad itself that connects to the pad, PAD, right, terminal on whatever our IO cell is. Then inside we have these power rings. Okay, so we have 4 rails over here. 2 of them are for IO power and ground. So remember that our IO voltage is often going to be higher than our core voltage, and it has an IO ground associated with it. A lot of times the IO ground and the core ground are going to be shorted together, but you can separate them to provide lower noise and so forth on this power domain. Okay, then we have the digital ground and the digital power. They're going to be called VDD and VSS versus VDD IO and VSS IO. Again, VSS and VSS IO are most often shorted together, but they can be separated. VDD is a lower voltage than VDD IO, and we have both of them. And these are going to be connected inside. There are going to be these stripes here inside every single one of our IOs, and we'll see why in a second. Okay, then we also have this other thing, at least in this IO library, called Power On Connect, and it's another type of a line that's going to be connected through all of our IO cells. And any types of other pins we have, they're going to be over here. So those C or I pins that we had, they're going to be on this side over here in whatever metal layer. And they are not connected to these rings, as you can see. So we then can build our whole IO ring, and this is a kind of a setup that we can have. We see we have 4 sides, and we have to make these connections. These are in what we call a corner cell. So our logic core is everything that's going to be inside, and then here are our rings. So what we have here, starting with this, is we have a VDD IO power cell. And that is just one of the types of cells we have in our library. And all it is, it takes our pad and it connects it to the VDD IO ring that's going to be now connected all around the IO ring, because as we saw before on the previous slide, every cell has this type of a wire that's through to the sides, and they're connected by abutment. So every one of these is connected to the next one. And if we have holes in here, we're going to actually fill it up with IO fillers, which are just cells that extend these wires from one side to another. Okay, then we have a ground supply cell. So in this case, we're going to have a combined one that shorts together VSS and VSS IO, and we see again it's a pad that's going to be connected externally to our ground level, and it's going to be connect to the VSS IO ring, and it's also going to connect to the VSS core VSS ring, and it's going to connect them together. Now you see that I also put several of these, both ground and VDD pads around the chip, because we need to supply as much power as needed for different things like simultaneous switching. Okay, then we also have what we call the core VDD digital supply cell. So that's going to be the same thing, but it's going to connect to the core VDD ring. And we also have a special cell that connects to the POC ring that we had before, so that's going to connect to this green guy over here. It's also going to be over here connected to our VDD IO, but it connects to the core, to the POC ring as well. So those are our power domains and our power supply cells. The next thing is, what if we have some sort of a power domain over here, an analog block that needs a special voltage? So what we're going to do is we're going to put an analog voltage connected over here and use an analog IO that, as I said, it's just a wire. This is not a buffer, it's not a digital block, it's just a wire that connects whatever voltage we brought in outside to our analog block over here that gets some sort of voltage that is not either VDD or ground. And this guy is going to be ESD protected, but it is not connected to any of these it's not going to be directly connected to VDD or ground. It's not going to drive a 0 or a 1. It's going to be ESD protected, but that's it. So let's go just jump over to the IO ring for a second, and what we can see here in the IO ring itself is all it is again that same type of interface with the wires that are going to the core. These are from the outside world, these are to the core. And again, it's the same inputs and outputs, and it's just a list of all the pads that we're using. So at the beginning we have the IOs like the VDDs and the VSSs. We have some special pads for the corners of the SoC, and then we have all the IOs themselves. So these we're going to have to go and deal with them in the back end, and they are connected to the different wires that go to the core. For each one, it's a single bit each. So that is the IO ring that is instantiated here inside the top level. And then we have another level which is called LP RISC-V, which is going to have the internals of what we call the SoC, which is just the core itself, the RISC-V core, and the two memories. So let's go into that level. And what we here have is, as I said, so it gets these wires that go to the core. They're going to connect to it. And inside here, it's pretty simple. All we basically have here is we have an instantiation of RISC-V core, which is the top level of the RISC-V core of the CPU, which gets a whole bunch of wires over here that are things that we brought in, and as well as the connections to the memories. And then we have instantiations of the memories. So now I want to just make a point about compiled memories or a memory compiler. So we can have memories by just discussing them in RTL, just writing basically some sort of register or something in our Verilog. And that would be what we would call a standard cell memory. The problem is that each of those bits is made up of a flip-flop, which is relatively large, and the routing becomes complex and so forth and so on. So what we usually use is what we call a compiled memory, which is a custom design type of a memory built on 60 SRAM cells usually. So a compiled memory is a large array of bit cells and is generated automatically. We have a memory compiler that does this. And when we do it, we can select all kinds of things and options about it. For instance, a compiled SRAM can have things like a built-in self-test unit that's connected to it. It can have error correction codes, and it can have redundancy, enabling us to swap out bad rows or bad columns. So these are different options that we would select in the memory compiler and produce them automatically. So a memory array might be folded for a better aspect ratio. So let's say we had 2,000 words of 16 bits. So if this is like 256 rows, right, and the whole thing would be 2,000 rows, but it's only 16 columns. This would be a very, very thin and long kind of tall skyscraper over here, and that's not very nice for our floor planning. And so what we would usually do is to fold this type of a thing, and we turn it into something like this, where we have 16 output bits from the 128 columns. So we need 16 bits to come out, but we're going to fold it in such a way so that every 256 rows, in this case, is a separate type of a bank, and what we need to do then is multiplex between all of them. So out of all of those 8 sets of 16 bits, we need to take out one set of those 16 bits, and that's called a muxing or a mux factor. So in our memory compilers, we can usually choose different types of foldings that can be applied to whatever size of an SRAM we want. And when we press the button on the memory compiler, it's going to go and generate all the views that we need, such as libs, lefts, even data sheets, and so forth, that we can use this in our whole place and route flow. So when we use these types of compiled memories, we're going to usually use a wrapper. So compiled memories, and in general, any other hard IPs, they have specific features and interfaces. They have different types of pins that are going to be special for them. Whatever vendor you bought them from or whatever group made them is going to give different names to the pins and so forth. So what we're usually going to do is provide a wrapper that's going to be a generic way with generic naming conventions and so forth. And then inside the wrapper, we're going to make the actual connections to the instances we have inside. In our example over here, we have the level that's called, or the file that's called lp-risc5 top.v. And what it does, it instantiates wrappers for both the instruction and data memories. And those wrappers are called SRAM, SP, which stands for single port, instr, which is instruction, and wrap for wrapper. So this is a single ported instruction memory wrapper, and the same thing for a data memory wrapper. So these are just generic, and then depending on whatever memory compiler we're going to use, we're going to have to go in and put in the memories, and we can also select the sizes and so forth. So they have real generic memory interfaces, clock, address, data, etc. Okay. In this case, we're going to have a second level of wrappers. And the reason we have a second level of wrappers is we have different SRAM cuts. So that's the actual size, the number of words, and number of bits that we have for each SRAM. And it really depends on what our memory compiler can spit out or how we decide to make them in order to fit in our floor plan and so forth. So just again, we're just abstracting away the cut sizes. So we can provide, we want those 2K words, and maybe we're going to do it with 2 blocks of 1K words. And so we can do that again generically without going into the specifics of what our naming signals and so forth are. So in the example, we have a 32K word data memory, and we make it with 2 16K word cuts. And we call these SRAM single ported 16384 by 32. That's the size. So that's 16K words of 32 bits. M16, that's a 16 mux factor. So there are going to be 16 words in one single row. BE, that means it's byte enabled, and it's a wrapper. So this is also another wrapper. It's a second level of wrapper, and it's generic. It is not specific to the actual SRAM compiler. It is, however, specific to the SRAM cut we made. So this is going to be a wrapper for a 16K by 32 SRAM. Okay, and the wrapper muxes the 2 cuts according to the address. So what the wrapper is going to do, we need 32K words, and it's going to basically mux the address into either one or the other, depending on what the MSB there of the address is. Okay, so it's another level that helps us kind of abstract away the actual implementation. Finally, we have a third wrapper that instantiates the SRAM, and this is called SRAM SP16 384 by 32.v, and inside we make the actual instantiation with all of the specific pins that our SRAM compiler connects to, and if we need to connect any constants or other things into there. So this is kind of a bit confusing, but I just wanted to show you how it is before I show it to you in the actual RTL. And so just as a higher level now of what we have in our entire SoC over here, so we have our RISC-V core over here. Okay, and it's connected to the data wrappers, and there are 2 of these data wrappers of 16K, which instantiate the actual 16K cuts inside. There are 2 of these wrappers of the instruction, the 16K instructions, or there could be more. Again, this depends on how you make it, with instantiations of the actual SRAM block inside. We have the IO ring level, and the IO ring has these actual digital IOs and power supplies and so forth, and they are connected to the external interface, which are called pad something. So we have, for example, pad clock will be the input of the clock to the chip, and pad done flag is the output of the when it says it's done with its operation. And then we have instantiations of the memories. So SRAM SP instruction wrapper, which we call it ICCM RAM wrapper. So ICCM would be the instruction memory, and we connect to a wrapper for that. And we have the same thing for the data wrapper, so that's DCCM RAM wrapper. And the module that we use is called SRAM SP data wrapper. And just for convenience, we have several levels of wrapping the memory, so we can kind of abstract away the actual implementation, what memory we have exactly inside, and let's see that. So if I take, for example, the data wrapper over here, so I go to SRAM spdatawrap.v, and that's going to be this first level of wrappers. So it gets these clock, data request, data address, data write enable, data byte enable, data write data, DS address select, and it outputs the read data out. Okay, so these are these general kind of buses that are accepted by the wrapper level, and inside, depending on what kind of SRAMs we actually made, we are going to divvy up these signals. So in this case, we are using a 16K by 4 with 4 bytes in each row. So it's a 16384 by 32 is the size of one memory block. So we created another level of wrapper called SRAM SP, that's for single port, 1634 by 32 MUX 16 byte enable wrap, and we created 2 of those in order to get actually twice as much memory over here. So what we have, this is 64 kilobytes of RAM, and we wanted to have 128, so we divided it into 2 different memories over here, memory instances. The first one we call DCC RAM 0, the second one we call DCC RAM 1, and basically we're going to give them the same addresses. So if we look at the addresses, it's going to get data address I 15 to 2 and data address I 15 to 2, as you can see here. The difference is that the chip enable of this, which is going to enable it or not, is going to be set by the 16th or the 17th bit. So data address I16, if it's a 0, it's going to go into this one is going to be enabled. If it's a 1, then this one is going to be enabled, and that's by this little bang that we have here and we don't have here in the chip enable. And the other thing is that the output of this, which is Q, the data R data, is going to be called 0 over here and called 1 over here. And then we're going to mux the 2 of those. So assign data R data out is going to be either this one or this one, the 0 or the 1, depending on this DS address select 0 bit that we have coming in. So that is just another level of wrapper. We still don't see the actual internals of how the SRAM itself is divided. We don't show anything about the exact technology and what the buses exactly go to the SRAM, but we imagine that it has a data, an address, and an output, and a clock, and so forth. So that they are abstracted away by this level of wrapper. So then I would go and I would look for, we've prepared several of these types. So if I just take one of them, like a 16384 by 32, and it doesn't really matter which one exactly this is the MUX 16 one. So this is actually, I think, the proper one that we had over there. So here I'm going to do the actual connection to the SRAM that I compiled already. So inside this, I'm going to get that simple interface that's kind of generic for any SRAM, and I'm going to go and instantiate the actual compiled SRAM I have over here, which I decided to call in the compiler SPHD 16384M16, and what I can see here is that I have, this generic thing that comes in with the wrapper, and all the rest are all kinds of pins that I'm not using in this specific implementation. So I connected them to all kinds of constants and unconnected outputs and so forth. But this is actually the SRAM that I have compiled already, and so this will be the interface of the actual SRAM. So that's just 3 levels of wrapping that I did to show this. Okay, the last part of the SoC, and I'll go back and overview this in a second again, is over here inside RISC-V master. I'm going to go and open RISC-V core, which is the other thing that I instantiated inside. This is the top level of the RISC-V core, and we can see over here that I have clock, reset, clock enable, test enable, boot address, core ID, and cluster ID, which are pretty much constants. And then I have request out, and I have address out, our data in. I have the different types of interfaces. Here's the interface to the data memory. Here's the interrupts, debug interface, CPU control signals, so forth. And then I start going on and doing what needs to be done inside the actual core to the different stages and so forth. So this is downloaded from the Pulp website, and it's a pretty clear, simple type of an embedded core. Okay, so now I'm going to go quickly over what we just saw again. So inside the SoC, I have my top level, which is LP RISC-V top. And so module LP RISC-V top over here, that's going to be the name of our design, the top level of our design. And The interface of this thing is all of these pins that start, or ports that start with the word pad, and those are going to be our inputs or outputs, our IOs to our design. They're going to be, you know, the top level ones. And all I have actually inside this module is an instantiation of the IO ring, which is a definition of specifically, if I go into IO ring, it's specifically instantiations of IOs that connect a wire from the outside, that pad, whatever, to a wire on the inside that's going to go to the rest of the SoC. That's going to come back to the SoC level. And then that calls another level which we have down here called LP RISC-V. It's just a little bit of another wrapper level. LP RISC-V has three basic things. It has the RISC-V core. So somewhere over here, I have my RISC-V core over here. That's the RISC-V core. It's going to get all those, or some of those wires that came in from the pads and other wires that are connected between it to the instruction memory and data memory. And it's going to have an instantiation of the instruction memory, and it's going to have an instantiation of the data memory. These both just have two other layers of abstraction of wrappers to take away, so I don't have to discuss exactly what the ports are and what the size of is the SRAM. I can use kind of generic signals, and depending on how much memory I want to put in and who the provider is of the actual block of memory, I put those inside these different wrapper levels to abstract it away and make changing these things a bit easier. Okay, so that is all I have in my SoC.